In this video, we'll be investigating a model of the revenue generated by a YouTube video as an application to review the most important concepts of calculus. In particular, we'll be working with this function right here. It is a function in the variable t, which represents the time elapsed since a video was uploaded. The output of this function represents the gathered views on a specific day after release, in multiples of 1000. For example, f of t is equal to 10 will return roughly 5, meaning that on the 10th day after release, this video will receive roughly 5000 views. And to convert from views to revenue, we use the conversion rate of 1.5 USD per 1000 views. Now, why this particular function, you may ask? Well, as we'll shortly see, it nicely represents the behavior of a spike of views in the first couple of days after release and then a slow decay as time goes on. Given this function, we now want to use our calculus tools to answer the following questions. 1. When do we get the highest amount of daily views? Or in other words, what is our maximum revenue in one single day? 2. How much revenue have we accrued after 30 days? Meaning, what is the cumulative amount of views after 30 days? And third, after how many days have we gotten 90% of the total views a video will typically get throughout its lifetime? To solve these questions, we will need to apply our knowledge of function graphs, derivatives, integrals and limits. And as always, the timestamps of each section can be found in the comments below, where you can also ask any questions you might have along the way. And with that said, let's get right into it. First things first, let's visualize the formula that we have in order to get a better understanding of why it models the behavior of the daily views. And it will also help us greatly to find the answer to our three problems. And just as a recap, our function of our daily views was v of t is equal to 10 times t multiplied by e to the power of minus 0.3 times t. And to visualize this function, we of course first need to draw our graphs. On the x-axis we have t, the amount of time after release, and on the y-axis we have the current views. Now, how do we intuitively plot this complicated looking function? Well, we see that it basically is composed of two functions that are multiplied to each other. On the one hand, we have 10 times t, and on the other hand, we have e to the power of minus 0.3 times t. And when we have such a composite function that consists of the multiplication of two functions, we can do the following trick in order to get a rough idea how the function looks like. What we do in this case is draw both of our functions on our graph. The first function is 10 times t, which is just a linear function with a slope 10. And the second function is an exponential with a negative exponent, meaning that it decays exponentially. So it never exactly reaches 0. And to draw our composite function now, which is the multiplication of these two functions, we draw a function that smoothly connects both of our functions. When t is very small, it will follow this blue dotted line, the 10t function. However, when t increases, the function will be dominated by this decaying exponential, and thereby it will be following this red dotted line. And from this simple sketch of our function, we can already see the expected behavior of the amount of views of a video throughout time. We see that in the first few days, there is a steep peak of number of daily views. And this peak represents all of the subscribers that watch the video when they get the notification. And then the period after this, there will be a slow decay of daily views. And it is this behavior that we will now investigate and which will guide us through our three problems. And the first of our problems was to find the time at which we have the maximum daily views. Now, since we have our visual representation, we can see that it will be somewhere around this time step right here. Let's call it capital T, because we see that at this point, our graph is at its maximum, meaning we have at this point the maximum daily views. Now, to actually get this time t, we will have to do some calculations. And this is a perfect example of an extremum problem, because we see that when we have our maximum daily views, that our graph reaches its maximum. Now we can also see that this happens when the slope of the graph is equal to 0, meaning a horizontal slope. But we also know that the slope of a graph is equal to its derivative. And therefore, if the graph reaches its maximum, this means that the slope will be 0 or that the derivative of this function is equal to 0. Therefore, we can translate our problem of finding the time at which we have the maximum daily views to finding t such that the derivative of our function is equal to 0. And that's exactly what we will do now. So we have that d over dt of our function v of t, or daily views, has to be 0. And this is the equation that we have to solve. And to do this, of course, we first have to take this derivative of our function. And to remind ourselves, our function was simply 10 times t times e to the power of minus 0.3 times t. And as we had identified while visualizing this function, we see that it is the product of two functions, 10 times t multiplied by this exponent. Therefore, we need to take the derivative of a product of two functions. We first just write our one function, and we multiply this with the derivative of our second function, which is e to the power of minus 0.3 times t. And then we add to this the derivative of our first function, which in this case is simply 10 times t, multiplied with our second function, e to the power of minus 0.3 times t. And these derivatives can be very easily calculated. So we have 10 multiplied by t, multiplied by the derivative of this e power. And the derivative of this e power is simply this e power itself. And we have to take into account a chain rule. So we multiply by this factor in front of the t inside of this exponent, minus 0.3. Then we add to this second term. So we have the derivative of 10 times t, which is simply 10, and we multiply with our exponent e to the power of minus 0.3 times t. And let us remind ourselves of what we are doing, that this derivative has to be equal to 0 in order to find the maximum. So let's rewrite this then by taking out some common factors in both of these terms. We see that we have 10 as a common factor, and this exponent is also a common factor. So we can write this outside the bracket, so 10 times e to the power of minus 0.3 t multiplied by what is left. In this term, we simply have 1 left, and in this term we have minus 0.3 multiplied by t. And now we need to find the specific t for which this is equal to 0. And of course we see that this is only possible when this factor here is 0. So we know that what needs to be 0 is 1 minus 0.3 t, and rewriting this even further, we get of course that t has to be equal to 10 divided by 3. And this is exactly our result. And we know that this is roughly 3.34 days after release that we actually reach the peak of our daily views, and therefore the peak of our revenue. Now, if we want to know the actual number of views on this specific time step, so the maximum number of momentary views, then we simply plug this number, t is equal to 10 divided by 3, into our function which describes the number of views. And if we do this calculation, then we find the maximum number of momentary views. And this would be v of t is equal to 10 divided by 3, which turns out to be roughly 12.2. And if we remember that this function represents the number of views in multiples of 1000, that would mean that we have 2.2k views at this moment. And if we use the conversion factor of 1.5 per 1000 views, then that would give us $18.3 at the maximum daily views. And after this warm-up exercise, where we basically just had to calculate the derivative, let's go to a more involved one, where we have to calculate the number of views after 30 days. And to tackle this problem, let's first look again at our graphical representation of the function. We had this sudden peak and then a slow exponential decay of views. And what we want to answer in this exercise is the number of views that we have after t is equal to 30. And as you probably suspected, this boils down to calculating the area under the curve from 0 all the way up to 30. Now, why exactly is this? Well, we remind ourselves that each point on this graph is the total number of views at that specific moment. And therefore, if we want to know the total number of views up to t is equal to 30, we need to add all of these values together. And since we're dealing here with a continuous function, this means taking the integral from 0 all the way up to 30, which corresponds to the area under the curve. Therefore, we can write this in a formula. We have that v30, which is the total number of views after 30 days, is equal to the integral from 0 to 30 of exactly our function again. And now what is left to do is simply to calculate this integral. But before we dive headfirst into the calculations, let me introduce one twist to it, just to generalize it a bit, which will help us a lot in the following exercises. Instead of focusing and fixing this end time to be 30 days, let's take it to be a variable capital T, which basically is a line that we can shift around such that we are effectively getting a formula for the total number of views for an arbitrary number of days, capital T. Now, the only thing that changes in our mathematical expression is that this upper boundary does not become 30, but simply capital T. And of course, this notation also changes, which becomes Vt, the total number of views after time capital T. And with this out of the way, let's now simply calculate this integral. So we have the integral from 0 to capital T of the following function: 10 times t times e to the power of minus 0.3 t dt. And again, what we see is that we have a product of two functions. And if we have to calculate an integral of the product of two functions, the first thing that comes to mind is, of course, partial integration. And that is exactly how we will solve this integral. First, we identify the two parts of our partial integration. Our function u will simply be 10 multiplied by t. And differentiating both sides, we get that du will be equal to 10 times dt. So the first function we already have down. And now the second one, the one that remains, will be of course our dw, which will be equal to e to the power of minus 0.3 t, which in turn means that w itself will be equal to the integral of dw. And with dw being e to the power of minus 0.3 times t, this integral can be calculated to be equal to 1 over minus 0.3 multiplied simply by this exponent again. And now that we have all of these four parts, we can simply fill this in the formula of partial integration. And if you're not familiar with partial integration, I gladly refer you to my video where I specifically solve exercises on partial integration. So we get the following. We get u multiplied by w, filled in the boundaries 0 and capital T, minus the integral within these same boundaries of the function w times du. And knowing all of these four quantities, we can simply fill this right in and calculate our integral. So this simply becomes u, which was equal to 10 times t, multiplied by w, which was equal to 1 divided by minus 0.3, multiplied by this exponent. And we fill this in the boundaries 0 and capital T. And we subtract from this the integral from 0 to t of w again. So 1 divided by minus 0.3 e to the power of minus 0.3 t multiplied by du. And du was simply 10 times dt. Rewriting this, we get the following. We have 10 multiplied by minus 10 divided by 3, which is 1 over minus 0.3, multiplied by the following. We have t multiplied by e to the power of minus 0.3 t, filled in 0 and capital T, minus this integral, in which we first take out these constant terms in front of the integral. So we get 10 multiplied by, again, minus 10 divided by 3, multiplied by the integral from 0 to capital T of e to the power of minus 0.3t dt. And this is already a very straightforward integral to calculate. This becomes minus 100 divided by 3 multiplied by the following. If we fill in t in this function, we simply get capital T multiplied by e to the power minus 0.3 times capital T. If we fill in 0 in this function, then we simply get, well, 0, because we multiply by t, and t is 0. So this term can be dropped, and we simply have this result for this first term right here. Then we have 10 multiplied by minus 10 over 3. These two minus signs become a plus sign, and we have 100 divided by 3. Then solving this integral right here, we first multiply this dt with minus 0.3. In that way, we have the same variable that we're integrating over as we have in this exponent. This is basically a very short way of doing substitution. However, multiplying this dt with minus 0.3 means that we have to divide it also in front of the integral. So we divide by minus 0.3. And this integral then simply becomes from 0 to t e to the power of minus 0.3 t times d of minus 0.3 t. And this now basically simply is the integral of an exponent. Rewriting this, we get minus 100 divided by 3 times t times e to the power of minus 0.3 capital T minus 1000 divided by 9, since we multiply 100 divided by 3 times 10 divided by 3, multiplied with the integral of this exponent. And this simply becomes this exponent again, so e to the power of minus 0.3 multiplied by t, and this we fill in 0 and capital T. And the integration part is already done now. Rewriting this, we get again this 100 divided by 3 capital T times e to the power minus 0.3 capital T minus 1000 divided by 9 multiplied by filling in t and 0 in this e power. If we fill in t, we have e to the power of minus 0.3 capital T. And if we fill in 0, we have e to the power of 0, which is of course simply 1. And in the end, we can rewrite this even further in order to get v of capital T, the cumulative amount of views after a time capital T after release, which is equal to 100 divided by 3, which we factor out, multiply by 10 divided by 3, minus capital T plus 10 divided by 3, and these brackets multiplied by e to the power of minus 0.3 capital T. And this is actually a very neat formula, because we can simply fill in capital T, any capital T that we like, and we receive back the total cumulative number of views after this specific time t. So if we return to our original problem, where t is equal to 30, then we can simply fill in capital T is equal to 30 in this equation right here, and we get the answer to our question. And the answer to our question is v of 30, which is roughly equal to 110. Going to views now, this means that we get 110,000 views after 30 days, and converted to revenue gives us approximately $165 after the first month of uploading this video. And to finish off, we go to the last exercise, or the last problem, where we want to calculate after how many days have we reached 90% of the number of total views that we can expect from this video. This of course translates to knowing the amount of time after release that we have gotten 90% of the revenue that we can realistically expect from this video. Now, the first part of this question comes from the observation that if we want to know when we are at 90% of the total number of views of the life cycle of this video, we need to know the total number, or 100% of the total number of views that we can expect in the lifetime of this video. And this is where our work on the previous exercise pays off, because the total lifetime number of views of this video is of course the number of views when we let capital T go to plus infinity, namely the number of views when the number of days after release becomes very, very large. And luckily in the previous exercise, we did some extra work to find the general formula to calculate the number of views after a general time capital T after release. We found that this formula, V of capital T, to be 100 divided by 3 multiplied by 10 divided by 3 minus the following bracket, capital T plus 10 divided by 3 multiplied by this exponent e to the power of minus 0.3 times t. Now, if you want that t goes to infinity to find the total lifetime number of views of this video, what we need to do is to take a limit, namely the limit of t going to infinity of this entire function. And why do we take the limit? Well, simply filling in t is equal to infinity, we get an infinite number here, but we multiply by 0, since e to the power of minus infinity becomes 0. And then we get 0 multiplied by infinity, which doesn't help us very much. Therefore, we take the limit of t going to infinity. And we see again here that we get two terms. We have this 100 divided by 3 multiplied by this 10 divided by 3, and we have this 100 divided by 3 multiplied with this term right here. And since the limit is a linear operation, we can split this minus sign of this overall limit into two limits. So we have the limit of t going to plus infinity of this first term, 100 divided by 3 multiplied by 10 divided by 3. And we subtract from this the other limit, the limit of t going to infinity of 100 divided by 3 multiplied by minus t plus 10 over 3 multiplied by this exponent right here. And we immediately see that in this first part there is no t, so this limit can simply be dropped. So we multiply these two numbers together and we get 1000 divided by 9. In the second limit we can pull this number in front of it and also this minus sign, and therefore we get plus 100 divided by 3 multiplied by the limit of t going to infinity of the following function. We have t plus 10 divided by 3 divided by e to the power of 0.3 t. And why did I write it like this? Well, because at this point you might see a pattern emerging. If we fill in t is equal to infinity, then we get infinity in the numerator, and in the denominator we also get infinity, since if we fill in this t is equal to plus infinity, we also get infinity. And infinity divided by infinity inside of a limit cries, of course, for L'Hopital. So we will use L'Hopital's rule to solve this limit. This gives us that v of t goes to infinity, so the total number of views of this video is equal to 1000 divided by 9 plus 100 divided by 3 times the limit of t going to infinity, but now using L'Hopital's rule. And what L'Hopital's rule says is that we now derive the numerator and the denominator separately and then take the limit again. Deriving the numerator, we simply get the derivative of t, which is of course equal to 1. And we divide this by the derivative of e to the power of 0.3 times t, which of course with the chain rule becomes 0.3 multiplied again by this e to the power of 0.3 times t. And then at this point we again take the limit. We see that if t goes to infinity, that in the numerator t has vanished completely, so we simply have this 1. However, in the denominator this t is still appearing. And this means that in the limit of t going to infinity, this term right here becomes 1 divided by infinity, which of course tends to 0. And this means that this whole term here cancels out. It simply becomes 0 in this large limit. This of course means that we are left with 1000 divided by 9. And to remind ourselves, this is the total number of views that we can expect from this video, which is roughly 111k views for this particular video. This of course directly brings us to the second part of this exercise, which is finding t, the number of days after release, at which we are at 90% of the total views. And since at this point we have the total number of views, namely v when t goes to infinity, or 1000 divided by 9, we can simply find t. So how will we do this very last exercise? Well, we need to find the total number of views after a certain time t, which is unknown. But we know that this total number of views will have to be 90% of the total number of views. So 90% of v when t goes to infinity. And we know, of course, that this is equal to 0.9 multiplied by 1000 divided by 9, the number that we calculated in the previous part. And since 0.9 is equal to 9 divided by 10, and we multiply by 1000 divided by 9, we simply get equal to 100. So writing this differently, we need to find v of a time that is unknown, which is equal to 100. And this is the equation that we will need to solve, because again, our work in the previous part pays off, where we have found an exact formula for this v of t, this total number of views after a specific time t. And that is of course exactly what we will be using right now. So we get the following. We get 100 divided by 3 multiplied by 10 divided by 3 minus this function 10 divided by 3 plus t multiplied by this exponent, and we close the brackets. And this has to be equal to 100. And what we need to find now is this t. So what we can immediately do is cancel this 100 on both sides of the equality sign. So this simply becomes 1. And we multiply this 3 away and put it on the other side. So this simply becomes, we need to find a t such that 3 is equal to 10 divided by 3 minus t plus 10 divided by 3 times this e to the power of minus 0.3 t. Rewriting this even further, we get the following. 1 over 3 has to be equal to e to the power of minus 0.3 t multiplied by t plus 10 divided by 3. Or written differently, we get the following. That 1 has to be equal to 3 times e to the power of minus 0.3 t multiplied by t plus 10 divided by 3. And it is this equation now that we have landed. And we need to find this t such that this equality sign holds true. And unfortunately, I am not able to solve this equation analytically, meaning with pen and paper. However, if you plug this into a numerical engine, then we get that this equation is true for t approximately equal to 13. And this means that 90% of the views or the revenue of this video is already achieved after just 13 days. And let's now summarize everything that we found in one simple graph. So we found that our graph looks something like this, a steep peak and an exponential decline. We know that our maximum was reached after just 3.3 days. We know that 90% of the total revenue was reached after only 13 days, which means that the area under the curve on the left of 13 days represents 90% of the total area under the curve. And we also know that the total area under the curve, which represents 100%, is roughly 101,000 views. And all of this with the power of calculus. And this brings us to the end of this quite long video. However, I hope that it was a very nice application and review exercise of the tools you have in calculus. If you like this video, give it a thumbs up. If you want to see more in the future, consider subscribing. And with that, I thank you for watching and I will see you in the next one. Bye.